Okay, actually, after you understand all about the normal distribution and standardized normal distribution, and then what is the parametric or the parameter of the population. So we have three types of parameters, right? The mean, then variance, and proportion. Okay, and for those three, we can do inference. So what is called statistic inference means we make conclusion or infer about the population parameter from the information about those parameters from samples. Okay, so population parameter means we use notation mu, variance sigma, and proportion P, capital P. And for sample, for mean, we use X bar, and then S for the actually variance is sigma square. So for sample S, and if only sigma, this is standard deviation. So S is standard deviation. P, so for sample, this is the small letter p for parameter proportion. Okay. And what we call inference is when we have this p, we infer about the, or we make conclusion about the parameter population. Okay, and that in statistic inference, statistical inference, we use distribution. For mean, we use standardized normal distribution, and for variance we use chi-square and f-square, f distribution. For mean, standardized normal distribution, and t distribution or student t distribution. For variance, chi-square and f distribution, and for proportion we use binomial, and standardized normal distribution. That's why it is called the parametric hypothesis testing. Because next week we start to discuss about non-parametric hypothesis testing. the reason why we call it parametric distribution testing, because it parametric hypothesis testing, because we use the approach of distribution. Okay. And specifically for hypothesis testing, for mean, for me, we simply use the we have two conditions. First, for one sample, and then for two sample. Okay. For one sample, we again divide it into two. First is when the variance is known, variance population is known, and the second is variance population is unknown. Okay. When the variance population known, we can simply use this C or standardized normal distribution. When the variance of population is unknown, we can use the T distribution. The formulations is x bar min mu null and divided by sigma per number of samples. And for T, actually the same, x bar min mu null, but since the variance population is unknown, so we use the variance or the standard deviation of sample, and divided by variance standard deviation of sample per square root of number of samples. Okay. So when and how to use it? First, the step. We use the step of hypothesis. So first define the objective, like what is the problem. This can be present by like write all the information. For example, like information about the expert, and then information about the mu null is the hypothesis, expert is the mean of samples, and mu null is the hypothesis of mean, population mean. And then n is number of sample, then sigma or s is the standard deviation of population known, means you can write down about the mean, about the standard deviation of population. But if it is unknown, you just can use the standard deviation of sample. Once again, don't forget that only sigma or only s is standard deviation, but if the information is the variance, mean it's the sigma squared is variance, and s squared is also variance, but this is for sample, for population, and s squared is for the sample. Okay, then the next step is write the hypothesis. So what is the null hypothesis and what is the alternative hypothesis? The null hypothesis always use equal to, because y equal to is based on the unguilty or positive mindset of the hypothesis. And for the alternative hypothesis, it's always like more than can be equal to, or less than, also less than equal to, or not equal. Okay. Okay, and then the next step is just define the alpha. And also compute the z or t, and then based on z and t you can define p value. The last two steps compare the z with the z alpha, or p value with the alpha.
Sorry, for the third procedure, is it compute
the z and t using this formulation,
And then compare.
Then compare the result with the C from the calculation or computation, and compare with, if you use C, mean compare with the C alpha. But if you use P value, means how to say, you need to convert the C value or T value to the P value, because C is the so when we say C mean this number, or T, but if you use P value means the area. So this is C is on computation, and this is the P value. Means if you have the result of C, it will be shown here. So if you draw the conclusions based on C, means you need to convert the alpha into C alpha. Okay. So for example, the alpha 0.05 or is equal to 5%. The C alpha will be 1.65. So you can just compare the result of C computation with the C alpha. Okay. So if the result C computations is greater than C alpha, means what? Will you reject or fail to reject? Greater means here the Z alpha, for example, Z alpha is 106.5, and if greater, your result for Z computation from here is, for example, 2.23, because the when you move to the right side, the value will be greater. So it's like from here to here, 0 to the greater numbers, and the left side is the smaller number. So from the minus 3 point something to 0 to 3 point something. So if you find that the C you compute is greater than C alpha, what is the conclusions? Reject the null hypothesis. So on the other hand means if it is higher than Z alpha, you fail to reject the null hypothesis. sorry, equal to mu naught.
But the z computation is greater than z, why is it reject? Rejected null hypothesis. Why does it reject?
Fail to reject that. So actually in statistics, if you read the book or in some software, they just use reject or fail to reject. It's not too common to use accepting. When you just present or discuss, you can use the accept the null hypothesis or reject the null hypothesis, or reject null hypothesis, accepting the alternative hypothesis. But usually in the same meaning, but I'm not sure actually in English it's clearly the same or not, like because this is hypothesis, it's not like really accept, right? So, but yeah, it's not wrong to use the reject or rejecting or accepting the hypothesis. So when we say we reject null hypothesis, it also means we accept the alternative hypothesis, right? If we fail to reject or accepting null hypothesis, means we reject on the other way, we say that we reject the alternative hypothesis. Okay. So when we do hypothesis testing, actually only have two conditions for the result, whether it is rejecting null hypothesis or fail to reject null hypothesis. So when we say we reject null hypothesis, means we agree that the mu or the mean of populations is greater than mu null. Mu null is one number that's already defined, or the defined number, or it also can be means we agree that the mu is smaller than the mu null, or even it is not equal to the mu null. Okay. So that's the step. And when the variance or standard deviations of population is unknown, you can utilize the T distribution with the same step. Okay. So that's for the one sample. Before we move to two samples, let me clarify about the test. So actually we have three conditions. greater than mu is greater than mu null, means you test the right side of C graph standardized or C distribution graph. So you just compare your Z computation with the Z alpha. But if your alternative hypothesis is smaller than, so mu is smaller than the mu null, means you do the left side test of the C alpha. And since the C and T actually the same, Z is standardized normal distribution and student T distributions. The characteristic is they are bell-shaped, mean equal when you divide it into two sides. The left and the right side from the center is equal. Means the Z value is equal to the mean Z values. Okay. But if you do the non-equal, means you compare it both sides, means your alpha need to be divided into two. So don't forget, when you compare your alternative hypothesis is not equal to, means you need to divide it the alpha into two sides. The half sides for the left and the half one for the right side. Okay. Means the Z computation need to be compared to either smaller, means it alpha 2, or be larger than Z alpha 2 to reject null hypothesis.
Sorry, even if we do not divide it into two, so that means like it's not the same from left side and right side.
If the sign of let's say what of the alternative hypothesis not equal to, must be divided into two for the alpha.
In order to make it like the same.
Yeah. Because if not, you cannot use this sign to do the hypothesis testing. Okay. And this means check where the same the same concept for T test. The difference only when you read the table, and also sometimes the S will not be given. I just want to know because this actually already delivered to you in second semester, right? The probability theory course. So you know how to compute the standard deviation.
Yes.
What is the formulation?
For standard deviation.
Is it the same just when n is divided by 2?
No.
No,
And
it's-
divided by 2 is the average, right? So for example, if you have, I give you this value, for example, weight of 5, or just maybe height. Your height, Ahmed, 100, 76, 176, right? Okay. And you,
171.
71,
168.
68,
180.
180, 167.
76.
So, what is the variance and what is the standard deviation? Can you compute?
What is the
When you have this data, if I ask you how much the variance or what the standard deviation, how can you compute this number? If you use Excel or Excel, you can just simply write all this data, then use the formulations equal to standard deviation, just then track all this data information, you can get the number. But if you use manually, what is the formulation? Xy, Xe, Si minus X bar
Divided by
n
n minus.
for standard deviation, which is square root I mean X bar. Okay. Okay, this is for one sample. And for two samples, we should have two population, and then from these populations, actually the same. You want to know the mean. So you will have like mu for population 1 and mu for population 2. Okay. Usually we just want to know whether the gap is greater than a number. U null here is that the basis. Here. Okay. So when it's larger than 0, means U null is equal to 0. Or another way to declare this is population 1 is greater than population 2. And the other way to declare also is U null equal to 0 and mu 1 is smaller than mu 2. And for this mean mu 1 is equal to mu 2. But sometimes the deviations or the difference between these two populations, mean of populations also can be some other numbers. So can be, for example, the difference 1 or the difference is 2 or larger than 1 or larger than 2. Okay. The condition actually the same. So when we say populations, it will have means and also have the standard deviation or the population standard deviation. If the population of the standard deviation of population is known, we use Z test, Z statistical test. But if it is unknown, we use the T test. If the population standard deviations is known, we do not need to care about whether this is larger or smaller. So just simply use the C test. But when the standard deviation of population is unknown, actually we have some alternative like the possibility, because we don't know, the possibility is actually it is the same or it is not the same. For example, the conditions of about height, actually we don't know in basic or in real conditions, when you don't know the parameters of mean, the parameter population of mean, we ideally we will also not know about the variance of population, right? But to simplify, we can just assume based on the historical data, we can assume that maybe just the same with the last year or last 10 years data. So we can directly compute about infer or make conclusions about the mean of the population. Okay, but in real, actually, when we don't know about the mean of the populations, logically we cannot know the variance as well, right? But so in those conditions, we should do, or when we not assume, mean we should use the t-test. What is the examples for the equal? Even we don't know, but we can assume that this is equal. Variance, for example, when you say you want to know the height of students in UB and the height of you are the students entry of 2023 means, right? Your
Four.
when you join the UP in what year?
2021.
Was 2024.
24.
Oh yeah, last year. It's your third semester. Then you want to compare with the students from, for example, the ITB. Say, UP students 2024. Yes, the grade of ITB students. Because we come from the same nations, actually we can assume that even we don't know the variance, but it can be the same. Right? But if we compare or then we observe the height of, for example, the height from Indonesian student with the height from the European student is the same age, the variance can be different. Right? Or maybe compared to like your father's generation, because like you can see directly, maybe in the same age, your height and your father's height or even your grandfather's height can be different, right? In those generations and the generation nowadays, I think in average or in common, it's tend to be taller compared to like third, two or third generations before, because what you eat is very different with what they ate before. Okay, that's for the case or the examples when to use the equal variance and not equal variance. For the steps for hypothesis is actually the same. What make it difference only the declare of the hypothesis. So you need to know what is the, like before you declare the mu null, here you declare the d null. And then also the hypothesis is whether it's the difference of mu1 and mu2 less than d null or larger than d null or not equal to. And for the test, actually the same. Just when you make when the alternative hypothesis is less than, means it's the left side. So you compare the t, compute the t, you compute with the minus t alpha. And for larger than d null means the right side. So compare it with the t alpha. And if two sides, because it's not equal to, means you need to divide the alpha into 2. So compared to minus alpha divided into 2 for the left sides, and also the baseline for the right side is t alpha divided into 2. Okay. The difference between the when you know the whether you know the variance or not, it's from the calculations of standard deviations. So in this case, the standard deviation formulations no longer with only s minus xi minus x bar square, and then divided into n minus 1, but you need to use these formulations. Okay, and for the unknown, for the this one unknown but equal but unknown, you can use those SP, and then the degree of freedom is number of samples population 1 from population 1, number of samples from population 2 minus 2. But for not equal to and unknown, you just know you need to compute again for the degree of freedom. So my question is, when you use this degree of freedom, why the degree of freedom is very important to find? When this degree of freedom, actually it's not in the formulation of the t. When you compute the t, you don't need to use degree of freedom, right? In t. Also here, t, when you compute the t, you don't need to use degree of freedom. No degree of freedom in the formulations. So why you need to care or then define the degree of freedom?
Is it like because T has like pair, but for like variance it's not paired?
Okay, not that part, but maybe before I explain. Any other? information. So when you use this degree of freedom, why do you need to define difference? What? Do you remember how to read table T or T table? So what information you need to read the T table? So if you read the table, you just need to, it consists of this is the probability, right? This one, the this is the C, this is the probability or the P value, and here is the Z value. For T, it's different, so this is the alpha. This is the T value, and here is degree. Zero, 1, 2, 3, and 2. Okay, so actually you compute the degree of freedom just to get this number, and then you get the alpha. So this formulation and this one is only used, it's used to define the degree of freedom, and then this is used to define the T alpha, because T alpha degree of freedom, or T alpha divided into degree of freedom, or minus T alpha. And for the computation, you just need to use the standard deviation. Okay, another conditions for comparison of mean parameters is when the condition is pair observations. Pair observations mean you have the same sample. Actually, this is also two populations, but it only differentiate by the treatment. So, for example, you have you want to observe what is the effect of medicine. So, or for example, how effective the treatment of medications. So when you have some patients for sample, then you give for example the treatment to cure the aches, for example headaches, just or maybe for example the headaches. So you give some treatment. Maybe you want to how to cure headache without medicine. So the effect of for sleep, or maybe effect of the drinking coffee. So just drink coffee for the whole weeks, 2 liters of coffee. So you want to know the effects. So the same samples but give the different statement. So that's the pair of observations. So you just actually the same, because the step for the hypothesis testing the same, but the statistical test you just use this T, and the N just 1, because it's the same samples but different treatment. Okay. And for this condition, we just utilize the T statistical test. Okay. Let's take a look for the examples. I forget about the homework. It's only for 1 sample or 2 sample?
Only one row.
1 sample. Okay. So for the 2 samples, so for the examples of the 2 sample, when the variance of population is known. So when we have a product developer is interested in reducing frying time of a primer paint, so this have a processing of in manufacturing have one process called drying. So the engineer or the product developer is want to reduce the frying time. So there are 2 paint. that tested to kind of paint is used, and then want to observe whether it's a difference or not. So of course he will change the paint to the one that have the lower drying time, right? So it has two kind of paints, and then have different drying time. So from the experience, they assume that the variance or the standard deviations of the drying time is known, and for the first one, it is it's known, and they incidentally or just luckily have the same variance. That is, the variance is 8 minutes. Okay, and then for the first type of paint, it used the 10 sample. Also for the type the second paint, it's also used the 10 samples. And for the experiments, the result, the drying time average for type 1 is 121, and for the paint type 2 is 112. Okay. Then it wants to the question is here, what conclusion can be productively drawn about the effectiveness of the new ingredient using the alpha equal to 0.05. Okay, so first define that it's actually for the hypothesis null, the two type of paints have no difference for the drying time, so the deviation is equal to 0. And then because let's check the promise paint at this state, maybe they should reduce the drying time. Okay, so the formulation 1 is the paint type 1 is the standard paint they usually use, and the second one is the new one because it's have new ingredients. So actually naturally they will expect that the second one, the new ingredients, will have the shorter time of drying process, right? So means the alternative hypothesis is the first one is greater than the second one. Okay, like you see when you don't have the answers, you need to understand first about the case. Actually, in the case, nothing mentioned about that the mu1 is greater than mu2, right? It's just mentioned the case, the law. So you need to carefully understand the case and then define the alternative, because when you mistakenly declare the alternative hypothesis, of course the conclusions you draw will also mislead. Okay, Because here nothing mentioned is about the mu1 should be higher than or greater than the mu2. Okay, so then we can declare the hypothesis. Mean the null hypothesis, of course, mu1 equal to mu2 means the deviations is equal to 0, and the alternative hypothesis is mu1 should be greater than mu2, or the new ingredients have the faster in drying process, or means the processing time for the drying is lower. Okay, and just do the calculation for the statistic, Z statistic, and because we already know that the X bar for standard pain is 1, 2, 1, and the means, the average of the mean of the sample of processing time of the new ingredient is 112, and the deviations is 0, and then we can also compute for the variance and number of samples for both of samples. Okay, in this case, for the standard for the alpha is 0.05, and if you use the Z alpha, it's 1.645. Means you need to reject the null hypothesis when the result of p-value is greater than 0.05, or the Z computations or the Z statistic is greater than 1.645, because the alternative hypothesis is greater than, means the right side. So your Z, this is your area of rejection. Okay, and after you compute, the result is 2.52. So if you compare this 2.52 with the 1.645, means 252 is greater than, this is the C statistic, and then C alpha. Here the C alpha is 1.65. Your C statistic is 252. Here, right? Greater than, and in here is the area of rejections. Mean you need to reject the null hypothesis. So this is the result and the conclusions, and you need to declare that reject null hypothesis. For p-value, you need to check in Z table. So when you need to see here, when you have 2.52, so it should be 0.0. Here you will find that this 2.52 is 0.0059. Okay. So using p-value and also using the Z value, the result is reject hypothesis, null hypothesis. What is the practical interpretations of the inference means we can conclude that the new ingredients significantly improve the drying process. Means the drying processing time become lower than the standard paint. Right.
So, which one is more complicated? Is it the one sample or the two sample?
Two sample will be more complicated because you need to like interpret the questions. What kind of what is the deviations and what it is care about, like whether is want to know about the for example this the effect of the population parameters, whether it wants to know it's become lower or better, or then it's don't have any effect, something like that. Because like I said before, sometimes the case won't will not clearly define actually what kind of alternative hypothesis that it want to know, but you need to interpret from the case. Okay, for the another examples here. So an experiment was performed to compare the abrasive wear of two different laminated materials, and then 12 pieces of material 1 were tested by exposing each piece to a machine measuring wear, and then for the second type of materials, they used 10 sample, 10 pieces of material 2 with the similar test. So in this case, the test is the same, but the difference is, or the population is the type of materials. Okay, the sample of material 1 gave an average coat wear of 85 units, and with the standard deviation of 4, while the sample of two materials 2 give an average of 81 with standard deviations of 5 units. Then conclude that the abrasive wear of material 1 exceeds that of material 2 by more than 2 units. So in this case, the case before, they just want to know whether it equals or not. It's whether have the significant improvement, but not define exact deviations they want to know. So the d0 is 0, but here they already mentioned about the deviations. They want to clearly declare the deviation into 2 units. Okay, and so just do the inference statistic to make a conclusion about this case. Okay, so the case is just the abrasive wear of material 1 exceeds that of material 2 by more than 2 units. Okay, then in this case, the clue is clear. That's more than means you can just make the formulation of alternative hypothesis, and then the null hypothesis, of course, it will be equal to Q. Okay, and because it's unknown, for the variance. So you can just this one. Unknown but equal, right? Assume the population to be approximately normal with equal variance. Means you just can use the degree of freedom. You can define degree of freedom by using the formulation number of sample 1 plus number of sample 2 minus sample 2 minus by 2. Okay, means like 12 plus 10 minus 2, so it's become 20, because n1 plus n2 minus 2 is 12 plus 10 minus 2 is 10. This number you can use to read the table to get the T alpha degree of freedom, because for T you cannot only use alpha, but you need to define the degree of freedom. So T 0.05 and degree of freedom 20. Okay. So, and from the table, the degree of freedom 20 and alpha 0.05, the T the T value is 1.725, and the T statistic, you can just use the formulations, and the result is 04. Means you're right. T alpha 1, 0, 2, 5, and the T statistic is 1.04. Means it's fall in the accepting area. Means the conclusion is do not reject or fail to reject, which null hypothesis. And what is that mean? That means we cannot declare that the deviation of that two or that the material 2 abrasive wear is greater than material 2 more than 2 units. Okay. Okay, for the and this is for the hypothesis testing of 2 sample means, but for pair observations. You see here we have the same samples but with the different treatment. Okay, so this is the first treatment, and this is the second treatment. So you can declare step by step. Here the n number of sample is 15, and you need to compute the deviations of each treatment for each samples. So you can get the DI, and you need to compute for the average of DI. Okay, so you can just get this. The important again is you need to declare the alpha. You define the alpha, and the questions here is assuming that the population is level as time of inject of injection and 30 minutes are normally distributed, thus at the 0.05 level of signification. So whether the drug concentration are altered after 30 minutes means because it's not defined whether it wants to know it doesn't mention about want to know it's lower or greater than, means it's just want to know that the concentrations are altered, means not equal or have the significance effect, right, to the circulation level. So you means here we do the two sides test, means you need to divide it the alpha by 2, and then degree of freedoms and minus 1, 15 minus 4, 1 mean 14. So you need to find the t value for alpha divided into 2 with degree of freedoms. T 0.025 with degree of freedom 14, and then you can get the t value will be minus 2.45 on the left side, and then in the right side is 2.145 in the right side. Then for the standard deviations, because no information, means you need to compute the standard deviations of this data, and you can get 18.474. Okay, and get the statistic T result 2.006 and compare it, because it's greater than 2.06 is lower, right? Lower than 2145 means you fail to do not reject or fail to reject hypothesis. Mean the concentrations of drug in the air circulations will not alter after 30 minutes, or do not have any effects to the level of the level of circulations. Okay, that's for the population. The mean. Next week, we like actually the logic will be the same. Maybe hopefully next week we can discuss directly variance and also proportion. Okay, so the next 2 weeks, because we only have like another 3 weeks, right, before the midterm. So for the last 2 weeks, we will discuss about how to use, or in what condition we use the non-parametric, and what approach can we use to infer or draw conclusions of a parameter populations when it cannot be done by the distribution-based statistic test. think that's all for today. Maybe later, tomorrow, I will give you like some homework to do to just try first about the variance, hypothesis testing, and the proportion. So next week, I hope you already have the glimpse about what is the variance hypothesis testing and the proportion hypothesis testing. Okay, any questions?
Maybe how do we know that the conclusion means like there is some evidence, or maybe like there is strong evidence? How do we know that?
Okay.
Confidence?
The conclusions is drawn by the test result. Means if you actually the hypothesis, alternative hypothesis, that the one that show it's have the difference, right? Whether it's lower or like larger, or you don't care whether it is lower or larger. It's just difference, right? So the evidence, we have evidence when it falls into the rejection area. Sometimes in statistical, it will not say that it have difference but not strong when it maybe, for the example, for the last case, the p-value is only, it can be said strong because the p-value is 0.06. The comparison is 0.025, right? Because the alpha is divided by 2. But when it's, for example, the comparison is with the 0.05, not that high difference, not too significant, but actually it has difference, but maybe not strong enough. So you can say that it difference, but not need to be careful because for example, the area here, so it accepted or failed to reject because like this 0.06 and here is 0.05. But maybe when you add more samples, it can move to rejection area, or maybe also can be farther from the baseline on rejection or for rejections. So sometimes when you say it's strong or not strong also depends on the deviation of the difference between T alpha with the T statistic test result or C statistic result with the C alpha.
So maybe if I can conclude, like we differentiate it based on our belief, like is it maybe closer or maybe farther, like we can conclude that it's stronger maybe.
Yeah.
So for next week, for the assignments, we have to find or
I will
variance
give
results.
some case in Google Classroom. Just try some those cases, and then if have any questions you can discuss in next week. But the topic will be about the variance and proportion
Hypothesis testing.
for hypothesis testing, both 1 and 2 samples.
For example, we need to draw the graph.
That will be easier. Actually, it's not not a must. When you can just draw the important step, actually here. This one. So when you already get the computation, you can compare because you have like the statistic test minus 2.77, and then your T alpha, your freedom is minus 2.160, and by this you can already conclude that it's rejected null hypothesis. But sometimes it's easier when you draw the graph, so you can see that the minus 2.77 is on the right side. Okay. So the T alpha, the of the line is 2.6160, and your computation result is here, right? Minus 2 means it's fall into the rejection area. So it is easier for us to draw the conclusions when we see the graph. But if you find it okay by only this formulation, no need to draw the graph. Okay, any other questions?
All good.
Okay. And